Get started. Okay, so welcome everyone. This is INSE 6630. My name is Jeremy Clark. Maybe some of you are familiar faces, some of you maybe not. You can call me Jeremy. You can also call me Professor Clark, whatever you feel like. Okay, let me say a bit about what this course is, and then we'll go through the course outline, and then we'll start into the material. This course is what we call a slot course. So a slot course is, the topic of the course is up to the professor. So if the professor has some new course that we want to do, then what we'll do is we'll teach it under this course description, 6630. And then maybe if we teach it a couple times, students like it, it's popular, then it might get turned into a permanent course. So many years ago, I taught this course, and I taught it as a course about blockchain technology. So like Bitcoin, cryptocurrencies, and things like that. Taught it twice, it was popular, and then as a result, it got made into a permanent course, so now it's 6615, okay? So if you were to take this course and someone else from our department was sitting here, you could be learning about anything, okay? So like depending on what the professor's interests are. So does anyone actually know what this course is about? Or you're all just here to find out? Yeah, a few of you I'm sure do, but okay. All right, so it's going to be a surprise, right? So no one knows what it's going to be about. Okay, so what this course is going to be about is something called zero knowledge proofs. This is a cryptography topic, okay? So it's something that comes from the branch of cryptography. And myself and a lot of people in industry feel like this topic is kind of like the next blockchain. So imagine if 10 years ago I said, come take a course about Bitcoin and cryptocurrencies and blockchain, and you're like, I kind of heard about that, I read it in the news, this was a long time ago. That would probably be pretty valuable for you to have taken 10 years ago and to know something about that field. So this field, no one knows the future, you can't speculate or predict it, but a lot of the same companies that are investing in the blockchain space now are focused on this space. So there's a lot of money going into it. There's not a lot of students that have good background in this area, so it's also something you're sort of on the ground floor of learning something, okay? Now, the course will be a little difficult. Not difficult, it will be, so I know students always ask me, is there a lot of math? That's one question. This course will be a lot of math, okay? It's basically going to be a math course, more or less, okay? But the math is not going to be any heavier than, say, 6110 or 6120, which I'm sure a lot of you have taken, probably most of you have to take those courses because they're mandatory, or you will have to take them at some point. I'm going to walk you through the math, I'm going to simplify it, and I'll do everything I can to guide you through it. Okay, so I don't think it's going to be a problem, but I'm just going to tell you straight up that there will be a lot of math in this course. Okay? All right, the Moodle is now online as of 15 minutes ago, so apologies for not getting it up earlier. It's not completely filled in yet, but some of the main points are there, so I'll just go through. So I'm going to start with the course outline. So the topic for this year will be zero knowledge proofs, otherwise, and there's a specific kind of modern type of zero knowledge proofs called SNARKs, and that's what we'll be concentrated on. My email address is here, my website is here. We'll have office hours. Office hours are virtual, so it's just a Zoom link. The Zoom link is on Moodle. They're at 2 o'clock, so if you have a question, you just join the Zoom meeting. It's a one-on-one thing, it's not like a group session, so when you join, hopefully either you'll be put into a call with me directly, or you'll be put in a waiting room. That means there's some other students that are already there. Zoom doesn't really show you how many students are in the waiting room or how long you have to wait or anything like that, so you can just wait, and then you can ask the questions, okay? That said, I'm also available. We'll have a break about halfway through the class, and so you'll have 10 minutes to ask me questions. After class, I'll stick around if there's questions as well. I'm very happy to receive emails. So if you have a question, don't feel that you have to wait until office hours to ask it. If it's something that you can write out as opposed to like speaking it out, just send me an email when you think of it, and I'll answer the email. Okay. So office hours, usually there's not a lot of students that come to them, but anyways, it is there. It's one way of you being able to talk to me, but it's maybe not the most important way. There is also a chance I forget, so I try hard not to, but if you do join it and it says like waiting for hosts to connect, give it a couple minutes, but if I don't connect, then you can just send me an email and say, oh, I was waiting at your office hours, it seemed like maybe you forgot, and then I'll either get online right away or I'll say sorry and reschedule it. Also, if this time doesn't work for you, you can always schedule, you can ask for a Zoom meeting at a different time as well. Okay. Oh, and the other thing I'll say is it's not like an hour long, like it's like I'll log in at 2, I'll wait around for 5 minutes, and if no one's there, then I'll just leave kind of thing. So it's like a check-in at 2 thing. It's not like a 2 to 3 thing where you can drop in anytime you want. Okay, these are some of the things that we'll cover in this course. Probably mean nothing to you. Which is fine. We're going to go over it. It might look complicated, but I promise you that by the end of this course, you're going to understand what all of these things mean. All of them are building up to one brand of zero-knowledge technology. So I thought instead of trying to show you a bit of everything and not really understanding it, it would be better to do a deep dive on one. So the one that I chose is called Plonk. Plonk is pretty popular. And Plonk is also very adjustable or customizable. So even if you don't do Plonk as it was originally written, you can swap out this piece for this piece, or you can add efficiency by swapping this out. So once you understand Plonk, say from start to finish, it's going to be a lot easier. Even if you don't end up using it specifically, you use something different, you're going to be 90% of the way there just by understanding one. Okay. So we'll work on understanding this. There's no knowledge that you need, no prerequisites for the course. If you come in with cryptography like 610, it might help you like maybe in the first week or maybe the first 2 weeks, but then we're going to get into new stuff that you haven't seen before. If you've taken 6120 with Amr, I know he covers zero knowledge. The way the stuff that he covers is kind of like what zero knowledge was in the 1990s. It also doesn't really help you understand what we're going to talk about. Okay, it will give you some of the intuition, but the way that we do it now, the modern SNARKs, like the way Plonk does it, is very different. It's a completely different approach to it. But there's no required textbook. I'll put some secondary references. So there might be like a textbook that covers what I'm covering or something like that. I'll just drop it there. It's not required reading. So the only thing you'll be tested on is the content of the lectures themselves. Anything there is just if you don't understand it, you can get second help. You can also use Gen AI like ChatGPT. It's very good. It knows about Plonk. It can explain any detail about it, probably in a very reliable way. You should always take a grain of salt with whatever it says, but I've talked to it about things that are way more complicated than Plonk, and it understands it. Yep, so Plonk is so let me give you an analogy first. So when I taught the blockchain course, I was like, let's look at one blockchain. So Bitcoin's the brand of a blockchain, yeah? So I said, let's study Bitcoin. So Plonk is to zero knowledge what Bitcoin is to a blockchain. It's one brand or protocol or system in order to do things. Okay. All right, the lecture notes. I'll say a bit about it. So this is my first time teaching it. Usually when I teach a course the first time, I do handwritten notes. And then later, once it kind of stabilizes and I kind of know what the content is and how long it takes to teach, then I'll make slides with it. So it will be handwritten. You'll receive a copy of whatever I write as a PDF, and it will be posted on Moodle. So you're free to take notes, but you're also free to just sit back and try and understand and follow, as opposed to making a copy of the exact same notes. I'm also recording the video right now, and the video will have what's on the screen, and it has my voice. And so that will get posted to YouTube, and I'll put that also on Moodle after every lecture. Okay, so if you miss a class, you can catch up by just watching the video. You'll have a copy of the notes as well. You can write over top of them or do whatever you want with them. The notes also slow me down. So sometimes with slides, especially with crypto, you know, there's lots of, I don't know, equations and messages going back and forth, and it's really easy for a professor to just sort of blow through it. This way I'm forced to like write out everything, and everything as I'm writing it, I'm going to be telling you what it is, okay? So it's going to slow me down, and it's going to make it hopefully easier for you to understand, because everything has to be written out. Grading scheme is pretty standard. We'll have a midterm. I'm not sure the week. It will be sometime either before or after reading week. It will be worth 20%. We'll write it in class. It will be more of a quiz. The main thing I want to do is just make sure that you're caught up to it. It's sort of like a way of forcing you to not fall behind, especially because I record all the lectures. It's very easy to say, oh, I'll watch those later, and in a couple weeks I'll just watch them and catch up on the course, which you can do, right? That's the benefit of having recorded lectures. But the downside is that you might procrastinate in doing that and things like that. So I like ideally I would have like quizzes all throughout, but it's too much work and it eats up a lot of class time. So we'll just do one midterm. It will be sometime in the middle. We'll write it in class. It might be just multiple choice. I'm not sure. We'll see how it is. But multiple choice is easiest for me to mark. There'll be a final. You'll have a project, which I'll talk about in a second. And we'll do either one or two assignments. So I haven't decided yet on what it is. I think we'll probably do 2 assignments. But yeah. Okay, this is a tentative schedule. It doesn't include the midterm, so the midterm will get slotted in sometime. And because I haven't taught this course before, I don't know how long these things take to teach. So maybe we go faster. There's lots of stuff to talk about. So if we get through everything quickly, there's a lot of different variations or alternative ways of doing things. And I will definitely get through all of Planck like before the course ends, for sure. There's some links to other stuff here. Okay, are there any questions about any of this?
So answer from the policy program.
Yeah.
So what do you think, like, how that is going for us? Is it because we never studied, as we said before, in other courses, just going to be something for us?
Okay, so there's no prerequisites for the course. And so whatever you, like, I'm not going to teach you high school math again, for example, right? So like there's going to be some concepts, but like to go into quality or to go into security, you basically come in with an undergrad in something that's technical. And so I don't really see a difference. Maybe the security people, because they've taken crypto and stuff, they're maybe a little more comfortable with the concepts, but it's a topic that's basically going to be new for everyone in the class. And there's not a lot that you've been taught before that's going to give you a head start, I would say. So I wouldn't be that concerned with coming from quality. Yeah. Yes?
When you say math, what kind of math are we talking about?
Okay, so I'll write this out in a second, but I'll say it now. There's a couple different fields of math. A lot of the math you can kind of draw a black box around and say, I don't really understand how it works inside. I just kind of know how it behaves. Like these numbers go in and this kind of number comes out. So the one branch of math is, it comes from finite fields or number theory. And it basically talks about, writing down just integers, no decimals. It almost simplifies your life by working. It sounds complicated if you don't know what a finite field is, but it's a way of taking the math, simplifying it, getting rid of a decimal, getting rid of a fraction. You just have integers. The integers don't go all the way to infinity. They're within a restricted range. And you don't have complex numbers or anything like that, okay? So you kind of take numbers and you simplify them. And then we do a lot of the math in that kind of setting. And so that's the same setting that if you've taken 6110, you've looked at maybe something called Diffie-Hellman protocol or something like that. That was the protocol that invented that kind of field. Yeah. The other thing that we'll do is polynomials. So polynomials are really important. Planck, the P in Planck is polynomials. Polynomials, if you don't remember, it's fine, we'll go through them, but it's going to be the basic high school polynomials where it's just one variable. So like a parabola is a polynomial, or a quadratic function or something. Yeah, and so it's going to be like that type of stuff. The only difference is we're going to put it in that number theory setting. So the polynomials are just going to run over the integers. There's going to be no decimals, no in-between points. The polynomials will be limited in size. And so it's going to simplify. It's even simpler than normal polynomials. Yeah? And then we'll cover like interpolation, like how you draw a polynomial through a set of points and things like that. And then we'll merge it with cryptography by one of the main primitives that we'll talk about is I have a polynomial, I'm thinking about it in my head. I'm going to give you kind of like a hash or like a fingerprint of what that polynomial is. And I'm going to be able to prove to you things about that polynomial. Like if you go to this polynomial, you open it, like you take the x value equals 17, then the y value is 20. And I'll be able to give a proof to you that that matches what I committed to. Yeah, that's the main thing that we need. And then once we have that, then we kind of build up a way of proving anything from that. So polynomials, number theory are the two. Other questions? Yeah. So I'll talk about that in a sec. I have a thing here. Yeah. Other questions aside from the project? Okay. Good. Okay, so I have a bit about the project, but the one thing that's missing is actually the answer to your question, which is the topic of the project. What I'm going to do is, because this field is sort of new, I think I'm going to try and steer you towards projects. So normally in my courses, it's just sort of like pick anything that's relevant. But in this case, I think I'm going to pick some actual topics. And I'll try and pick topics where you can think about either use cases, meaning like you don't have to do the math side of things. You just think about how are you going to apply to it. If you like the math, you can go in and make a math contribution. If you like coding or programming, then you can get a system that already exists, or you can try and code up something yourself that's able to do it. And so I have like one application or one use case of zero knowledge that I think is actually like pretty flexible, and you could do different research projects at different levels on it. Okay, but I need a few minutes or like a week to like kind of write it up. So I'll come back to you next week. That said, if there's a topic that you really want to do and you know that it fits under the umbrella of the course, you can do that topic too, but just ask me about it and I'll approve it. The projects will be a written report. That's it. If you do say you do some coding and you have code, don't put the code in the project. What you'll do is in the project is you'll write about what the code is. Then you'll have a link to where the code is, like on GitHub or something like that. So it will be a written report. Okay, so you can work individually or with pairs or groups. If you want more than 4 people for some reason, come talk to me. I find that I need to clear that. But if you want to work by yourself or up to a group of 4, you don't have to talk to me about doing that or who's in your group or anything like that. In general, in this project, there's no check-in. So you're not going to submit a progress report or a topic proposal or anything. Like the day that the project is due, I will get the PDF from you, and then that's it. We don't have to ever talk about your project beyond that. But I am here to answer your questions. I'm happy for you to talk about it, but we don't have to talk about it. I will, though, however, when I look at a project, I will consider how many people when I mark it. Okay? So if I see a project with 4 names, I expect the amount of work to be quadruple what I would expect from a single person as well. Okay? There's no advantage or disadvantage, I don't believe, to either trying to work alone or trying to work in a big group. Last year I marked a lot of projects for my other courses. I have the same policy, and some of the highest marks were projects of 4 people, and some of the highest marks were projects of 1 person. And so I don't think there's like there's any penalty to either working alone or to working with a group, okay? But if you do work for a group, you should try to find people that are going to complement your skills. And the main thing I'm trying to dissuade you from doing is one person writes a report and puts 3 names on it of their friends, because that's going to hurt you as the person who wrote the report, because it's not going to look like something that 4 people did. Question? Yeah.
When it comes to programming using existing frameworks, would you feel confident in saying that the language of CKVs is Rust?
So a lot of, so the predominant language is Rust. Yeah, so if you want to, not at the use case level, but if you want to go in and look at like libraries that do ZK stuff, I would say probably like, in terms of what people actually use, like 80-90% would be Rust. Yeah. And the reason for that is Rust like kind of became popular around the same time that zero knowledge SNARKs became popular. And there was also like a lot of people who work on this space, they also worked on the blockchain space. And Rust also started becoming popular in the blockchain space as well. So it sort of coincided in time, and so that's why it became prominent. Yeah. It also has some like safety features and things like that that can give you more confidence that the library is working the way you think it should. Yeah. Okay. Reports should be no longer than 8 pages. This is because I have 3 classes. I get final projects in all 3 classes, so I have to read 100 projects at the end of the year. And so I don't want super long projects. That said, let's say you have 8.5 pages because your references spill over or something like that. I don't care. It's fine. I'm not going to like take marks off because it's 8.5 pages or 9 pages or something like that. Okay. But if it's going to be 12 pages, send me an email ahead of time. Just tell me why you cannot possibly get it down to 8 pages. You need 12 pages, and then I'll say that's fine. Template anything you want. It doesn't matter. You can use the default Word, default Google Docs, default LaTeX, whatever you want. You don't need a cover page. Just make sure that that all the authors and their student numbers are on it, and the title, obviously, of it. Plagiarism. So plagiarism is where you take knowledge that exists, and you present it as if you came up with it, even though it already existed. So the clearest cut case of plagiarism would be if you find some text, you copy and you paste it into the document. You don't cite it. You're not like, this is text from this place. You're just presenting it as if it was something you wrote. So that would be considered plagiarism. A variant of it would be you would copy and paste it in, but then you would sort of change the grammar or change some of the words. But the meaning is still the same. The logic, the flow of what's being said is still the same. That's still considered plagiarism. So to avoid plagiarism, first off, you shouldn't copy and paste text in, even if you intend to rewrite it. Read it, close it, and then repeat it from memory. And then you can always go back and cross-check and make sure that you got everything, but it's better to sort of recite it from memory, because then you're using your own words to do it. You can't submit projects that you've submitted in other courses. You can't submit projects that other people have written in past years, although that won't apply to you because you're the first to do it. Moodle has some basic plagiarism detection. I don't rely on it, but it's either like if it says 30%, I just don't pay attention to it. But if it says 98% or something like that, and then I look at it and see, oh, this is the exact same report that was submitted last year, then that's a different scenario. The other thing is everything you do, you cite. So you just tell me where you found it. And you can do that when you're writing in a conversational style. You don't have to do it in a formal way. You just, the same way that like if I was talking to you and I said, where did you get that from? And you'd be like, oh, it's from this paper. You just write that into the paper itself. So you just say that, in this paper, these people proposed, these 5 rules, : and then you list the 5 rules. And now it's clear to me reading the paper that those aren't your 5 rules. You didn't make them up. They came from this paper. Okay, so just pretend you're having a conversation with me about like where you're learning stuff from, and then put it in. The citation itself, I don't care about format of the citation. As long as I can look at it and figure out, what you're talking about, then that's sufficient as well. Okay, questions about plagiarism or about the other stuff? Okay, the final thing is ChatGPT, Gen AI, those types of tools. So this is my policy. It only applies to this course. It's not a university policy. It's not a CIISE policy. If you take courses with other professors, they probably will have a different policy about this type of thing. My policy is you can use it for whatever you want, more or less, okay? But what I want from you is I want disclosure. So I want to know that you used it. I want to have a sort of brief overview of how you used it, like just in your own words, like maybe a paragraph or a sentence or two. And then what I'd ask for is that you only use tools that create a transcript or a copy of the conversation, and you include a link at the end of your paper to the actual transcript that you had. Okay? As long as you do those things, you disclose and you have the link to it. By the way, ChatGPT has links. That's the one I use. I think most of them do. Even if you find one that doesn't and you really want to use it for whatever reason, you can maybe copy and paste or export to a PDF or something like that. But anyways, as long as you do that, you will not get in trouble for anything. Okay? Even if you're like, hey, ChatGPT, here's a copy paste of the project description, write me a 12-page project, and you hand that in, okay? Now, you will not get a good mark, okay? So when I look at this, I am trying to understand how much you understand. That's the most important thing to me, okay? So if you're relying too much on it, and I'm not convinced that you understand it, you just are repeating things or having it write things for you, okay? Then you're not gonna get a good mark, but you won't get in trouble, you're not going to get, it's not plagiarism, it's not academic offense under this policy, okay? So you can do it any way that you want, but just know that when I mark it, I want to make sure that you understand it as well, okay? So I think I said everything, but anyways, so limit yourself to Gen AI tools that let you share a transcript, put a paragraph at the end of the paper. Even if you don't use it at all, just put a paragraph that says I didn't use it. And then have a link to all your transcripts, so you might have more than one. It's nicer if you just keep it in one window, so you make like the transcript for your project. Your grade is based on demonstrating that you understand your topic, and this is my policy. I should say, sorry, I copy and pasted this from my other course, but it's for this course as well. But I know that like lots of professors completely ban ChatGPT, which is fine, but it's just not realistic, I don't think. So. I'm also curious how students use it, right? You guys are younger than me, you probably use it in like cool ways that I haven't even thought about it, and so it's good to learn from you as well. I use it a lot, by the way. Okay, grading. So the main thing I will grade on is scope and execution is sort of like, what's your topic, and how do you decide like whether to include something or not include something? Do you do like really overview, high level, and then do a really deep dive on some like little point that no one cares about, and then go back to a high level? Like that is sort of not well executed. The topic, if I give it to you, then you're still going to pick a topic. It's going to be more like an area to study, and you're still going to pick your specific topic. So this somewhat applies, but it also is on me to give you a good scope for your project. Interpretation is like, when I read your report, the main thing I'm asking is just like, does the student understand it? It's easy to like repeat things without understanding it. Even if it's not copying or ChatGPT wrote it for you, even like I can read something well enough to repeat it, but I don't really understand it, right? I might make small mistakes, or I might not explain it well, or I might, miss things in my explanation. And so that's the main thing that I'm trying to gauge you on when I read your reports. So anything that you can do to signal that you understand is good. It's also perfectly okay, this is very applicable to this course, to say in a report, I don't understand this. There is this paper, it does this thing. The paper or system or blog post or whatever, it says that if you put this in, this is what comes out. I couldn't tell you how it works, right? It uses multivariate polynomials, and I have no idea what that is. Okay, that is fine. That's acceptable. You just tell me. You're not supposed to be zero knowledge geniuses at the end of this. Okay, you are going to know a lot more than you did at the day one, but you're not going to, compete with academics that have studied this for 10 years or longer. So that's fine. Technicality, probably won't have a problem with this in this course because it is sort of a more technical subject, but I'm looking for some level of technicality that would be appropriate for a graduate level. That could be math, it could be code, but it can also be like, even if you're just doing a use case, it's like you're clearly explaining things, you're not skipping over details. You know, things might get like tricky to explain, you're not like kind of hand waving it away. You're going to sweat the details and you're going to explain it. Even if it's tricky to explain, you'll find a way to explain it. So that's what technical means. It just means that you go through everything. Yeah. And then manuscript is just kind of like, you know, it should look nice. Sections and subsections, it makes sense. If you're using figures and tables, they should be appropriate, that kind of thing. I don't mark on spell check or anything like that. I know a lot of people are English second language, so that doesn't bother me if you are going to make mistakes. Although now with ChatGPT and things like that, I think a lot of people at least do a grammar check with it. Okay, that's what I wanted to say about the project. Topic I'll give you next week, but is there any questions about it? Yeah. Sorry, I'm having trouble hearing you. Oh, why is a project only worth 20%? I don't know. To me, it's one component. There's not a lot of thought that went into it, but you would expect it to be lower or higher? 6150, I didn't have a midterm, so that's the main difference. So here, because I have a midterm, I have to take weight away from something else in order to do it. So I think that's sort of the reason, is just that like your midterm is worth the same as your project, kind of, yeah.
Do you foresee there being a coding aspect to our projects? And if so, which programming languages do you think?
Okay. So programming is not mandatory. So there won't be a mandatory programming component. It will be an option though. So if you like programming, you can do something. And if you don't like it, you can get a project done without ever talking about it. Languages, there's two. So there was an earlier question. If you want to do, like say you want to implement the technology that we're talking about, like we'll talk about this Plonk and you want to implement it, or find an implementation of it, maybe change it or something like that. Most people use Rust. That's standard. The second way though that I see you using it is, we haven't got into the content yet, but what zero knowledge lets you do is it lets you prove anything about anything. And the way you specify it is by programming it. So there's zero knowledge languages, like languages where you say what you want your proof to be and you specify it. And those languages they're not a common programming language. They're not a general purpose programming language. They're like a restricted language just for that. And there's lots of different ones. The one that's like probably the most user-friendly is called Socrates, and it's JavaScript-esque, like in its notation. And so a lot of people, if they're just starting, you just sort of write out what you want in JavaScript, you press a button, and then it generates a proof and puts it on the blockchain or whatever you want it to do. Yeah, and then there's a bunch of other ones that you could use as well if you want to specify what you want. Yeah. Okay. Other questions about any of this? One other topic I almost forgot about because it's at the bottom is the final exam. So I'll talk obviously about the final exam, a week or two before the final exam itself, but this is what you should know today about it. First off, when is the exam? I don't choose that. It's chosen by the department or by the university. You can see the dates of when it will be with this link. So you can see April 16th, the exam period begins, and May 3rd, the examinations end. So your exam could literally be any time in that window. So if you're planning on doing some travel or something like that, wait until you get the exam schedule before you start booking tickets or do anything that you can't cancel or get out of it. Traveling's not an excuse for missing an exam. Usually it's like the week after on the same day. So like because we're a Thursday, it's usually like the first Thursday, but that's not necessarily a guarantee. Last term it didn't follow that rule. We had one exam that was like 2 weeks after exams began. So yeah, so anyways, just hold off on anything before then. Yeah.
Any tentative date for midterms?
So the midterm, I need to sit and internalize my calendar because I'm traveling around reading week and things like that. So it would either be, I'm not going to put it too early because there's not enough content. So like the earliest it would be is 1 week before reading week. And then the latest it would be is maybe 2 weeks after reading week because I think I'm traveling the week after reading week. But so normally I usually either do it the week before or the week after reading week. And then sometimes I do it two weeks after if I can't make it. Yeah.
The midterm be like the entire class?
Yeah, so the midterm will cover the lectures up to the midterm itself.
Yeah.
Maybe inclusive of the week directly before, maybe not. I'll make a judgment call on that, like to see where the cutoff is. And then the twin question to that is the final. The final will be comprehensive, so it will cover everything. I have to do it this way because sometimes students miss midterms and then they just write the final and I take their grade on the final and apply it to the midterm. And so the final has to cover the whole course. That's like a Concordia policy. But the emphasis would be on the midterm onward. But in this course, because it's going to build as well, if you don't know the sort of pre-midterm stuff, you're going to struggle with the post-midterm stuff as well. So, yeah.
I think I just asked my question a bit poorly.
Yeah.
Like the midterm take the entire class? Like,
Oh, sorry. Yeah.
my bad.
Probably not. So sometimes students have accessibility issues and they get a longer percentage. So I like to make it a little shorter so that they have the option of just staying in class and writing it if they don't want to write in the accessibility office. So I would probably, class is like 2.5 hours. I'd probably make it like an hour or something like that. Like it will be more of a quiz. It's really about a checkpoint, making sure that you're like kind of forcing you to catch up on the material. And I'm not going to try and do like a big long midterm. Yeah.
What's the latest by when the final exam date would be announced?
So it's sort of, I try and think about it every year and I forget to like take note of when they put it out, but it usually, like it's not going to come this month for sure. It will be February, but I feel like it's sort of like early mid-February. So you usually have like a couple months notice, but yeah, it's up to the university too. Okay, for the exam itself, short answer, true, false, multiple choice questions. You can write it in pencil. If we do multiple choice, you'll do it on a Scantron form. So that's like the separate form with the bubbles where you fill it in. It gets marked by machine, which is nice for me. This is the main thing that I want to mention. When you come in the exam, you can have a cheat sheet of 1 page. Okay, so front and back, as small as you want or as big as you want. So I'm not going to be testing you on memorization or did you memorize this or not memorize that. So anything you're worried about, like maybe I'm going to forget that in the exam, you can write on your cheat sheet and you can bring it in. Okay, so the exam will focus more on the concepts and applying the concepts and that type of thing. You can bring a dictionary if you want. This calculator, I say you do not need because I copy and pasted this from my other course. In this course, it's actually reasonable that maybe you might need a calculator. Like it would just be like addition or multiplication or something like that. But I'll revisit this later, but I think you probably won't need a calculator to do it. Oh yeah, and then when the schedule does come out, I think you probably get an email about it, but it's also on this page here. So you can see graduate exam schedule. So the exam schedule from last term is here. And so sometime, hopefully like mid-February, you'll see that link get updated to winter. And then you can see it. Okay, questions about any of this logistical stuff? I see no questions. Okay, that's good. Okay, so let me try and describe the course for you a bit. So the course calendar says like recent developments in security or something like that. But the topic will be zero knowledge. proofs. Thank you. Okay, so I'll just pitch you a bit on the high level of ZKP before we go into like sort of an overview of what it does like a little more concretely. Okay, so ZKP it's something that comes from cryptography. It was invented in the 1980s. However, in this class, we're going to focus on sort of a modern version of it. And it wasn't really until this modern version came out that people saw it as like a world-changing technology. So before it was always interesting, it was cool, but it was really slow and like kind of onerous, and it was too much work. And so people thought it was cool, but like wasn't really that useful. But now with the modern variant that we call SNARKs, people are like, okay, this is actually really useful, and we can use this for all sorts of different use cases. Okay, so every class, not today, but every class from now on, I will give you one use case. So we're going to spend the first part of class just talking about a use case, and then we'll spend the rest of the class talking about the theory and actually understanding how these things work under the hood. Okay, so every class will have a use case, and then it will also have some of the theory. All right, there's a lot of money in this space now. So lots of companies are putting money in. I think of it as kind of like akin to blockchain. In maybe, I don't know, like 2005 kind of thing. So it's kind of like people are seeing it as like the emerging area. And there's jobs in the area and not a lot of expertise. Another thing that will be useful to you is there's no shortage of content online that wants to explain it to you or talk about use cases. So once you start Googling around for this stuff, you'll find like millions of things about it. You may not know about it if you don't follow the space, but you'll see. So there's lots of content. And at all sorts of different levels. So you have your academic papers that even I don't understand, and then you have everything from that to one thing that I'll emphasize, actually for your assignment, I might make you actually just listen to it. But one good resource is there's a podcast called the ZK Podcast. This is run by someone actually from Montreal, though she lives, I think, in the US now. And she's not a cryptographer or an expert or anything like that. Okay, yet she has a podcast about zero knowledge every single week. It's audio, so there's no math equations, nothing's written down, it's only what you can say. And it's a lot of like the founders and like different people working, researchers and also like company entrepreneurs and stuff like that in the space. Every week there's an interview. Sometimes it's not strictly about zero knowledge, sometimes it's about blockchain or like some adjacent areas, but more or less it focuses on it. So it's a nice thing to like listen to. When I give you the project topics, they'll be like, I'll give you like 4 or 5 episodes about it, about the topic that you can listen to as well. Okay. So I already covered this, but because I know you're concerned about the math content, I'll give you my math disclaimer. Okay. So first off, there will be math. However, had you taken INSE 6110, you've also seen a lot of math. And I'm learning this because I'm teaching this for the first time this semester, by the way, which is why this course got moved to today. In 6120, there's actually a lot of math as well. Even zero knowledge proofs show up in here too, okay? So it's going to be like a similar level. What I promise you is I will explain everything as if you just have high school math. So I'm not going to just jump in and assume that you know what a finite field is or anything like that, okay? The second thing is that the math is super applied. So we only use the math because we have a problem that we want to solve, okay? There's no going to be, we're not going to sit around thinking about theorems or about generalizations of the math and things like that, okay? We have a problem that we want to solve. We need some math to do it. We're going to learn exactly the amount of math that we need to solve that problem. We're not going to learn any more or any less, okay? So it's going to be very applied. So it will do a narrow application. So I'm not going to teach you all number theory just so that you can learn the one thing that we need to know, or I'm not going to teach you all about polynomials just to learn the one thing that we need to know. So everything we use it because we need it. And I reflected also, I was like, if I was in your shoes, would I want to take this course or not? If the professor's like, it's going to be a lot of math. And so I was like kind of, as a student, there were some branches of math that I was terrible at. I don't know why, like probability, Bayes theorem, all that stuff, I could not understand. And then there was some stuff like, I don't know, vector calculus, where I got it. Like I understood it, right? And this won't necessarily apply to you, but I think it's fairly universal. But for me, when I reflect back and I think about why couldn't I do good in Bayes theorem, but I could do good in vector calculus, the difference was in vector calculus, I could visualize it. I could close my eyes and I could picture what was happening, and then I could understand it. In probability, I didn't know what does a probability look like. And when you think about conditional probabilities, like I don't have a visual for it, so I can't really see how they're doing it, okay? This content will be highly visual, okay? A lot of times we're going to draw things out and we're going to move things around and shuffle things and do things like that. We're going to circle, we're going to say, here's all the numbers that are possible and here's patterns that you can see and you can circle them and things like that, okay? So I think everything in this course, more or less, will be visualizable. So it makes it a lot easier. And the other thing is that this math is very friendly to small number examples. So in the real world with cryptography, we use huge numbers that you can't visualize just because they're too big, okay? But what you can do is you can limit Planck or any ZKP protocol, and you can talk about, like, I just want to talk about the numbers between 1 and 90 or 1 and 10 or whatever, right? And you can run the entire protocol just by looking at these really small numbers, okay? And so we're going to do a lot of that. So a lot of the equations and stuff that I show you will be paired with a working example, but it's going to be like small, like really small numbers, okay? But you can actually see everything that's going on, okay? Okay, they're so small that there's even a website, or I guess it's like a Medium post or something like that, where, let's see if I can. Maybe it got taken down. I'll try and find it and I'll try and put it on, this isn't what I was looking for. I'll try and find it and see if I can find a mirror of it or something and put it on Moodle. But somebody actually literally did the whole protocol by hand, on paper, pen and paper, with numbers, writing down the numbers, and you can kind of trace through the whole protocol. Now that article, I don't find it that good because it tells you what you're doing, but it doesn't really tell you why. It's just like, okay, you do this equation, but it doesn't tell you why. So in this course, I'm going to focus a lot on like why you want to do these things. But anyways. Okay, so that's my like sort of pledge to you about the math. So hopefully it might scare a few of you off, but hopefully not the whole class. Okay, any questions about this? Okay, Now let me try and shed some light on what a zero knowledge proof is. I'm not going to jump right to exactly what it is because it's a little weird, okay? But what I'm going to do is I'm going to try and build up some of the intuition for what it is, and then by the end of class I'll show you exactly what it is. Okay, so let me start with, just put on a new page. Okay, so what I have here is a simple function. And I have some inputs to the function. And I have output. Okay, so this class is all about this, basically. Okay, so we have just a simple function. What does a function mean? What is it? So functions, people use it different ways. So you can think of it more like a math object, or you can think of it kind of like a program or a circuit if you're an engineer. And so you're free to think about it any of those three ways. Okay, so it applies both ways. So you can think of it as like an equation or algorithm, maybe algorithm slightly different. You can think of it as a program. You can think of it as a circuit. Okay, it's basically something that does something. Okay, now one thing that this won't be is a full-fledged computer. So a computer is slightly different because a computer can store things in memory, and then it can come back later, and it can retrieve things from memory. It can sleep for a while and then wake up and then do something and then go back to sleep. Okay, so here what we're going to consider a function to be is it's a one-shot deal. You have your inputs, they're ready, they're available. You're going to do the computation on the inputs and you're going to get the output. So there's a clear start and a clear finish. Okay, so you just process it and then you're done. Okay, those are the functions that we care about here. Okay, so you can think of it kind of like a calculator. So f is it starts and finishes. Or sometimes we call it a one-shot function, like you do it. You can do the function as many times as you want, but every time is a discrete. Like you can change the inputs and run it again or whatever, but you're basically just going to spit out whatever you want. Another thing that we'll consider that's very important is f is going to be deterministic. What does that mean? Big word. It means that it always gives you the same output if you give it the same inputs. There's no randomness in it. Okay? So if you give it the exact same x and the exact same y, you're always going to get the same z back. Okay? Now, you might want randomness later when you realize why we're talking about these functions. You might say, oh, I really wish we had randomness for this function. It's fine, but you have to put the randomness as an input. Okay? So you can take some input that represents the randomness and then it will do it. But f itself is strictly deterministic. So the inputs map to the output. Okay. So let's say I give you this description of a function and I ask you to make something in real life and give it to me that's able to run a function like this. What would you do? What would you come to me with? Something that I want to be able to run this function. I want to be able to, I have some x's and y's, and I want to compute z, but I don't want to do it by hand. So I want you to give me something that would let me do this. Okay, so a calculator, what is a calculator if you open it up?
Circuits.
Circuits. Okay, so one thing you could do is you could give me a piece of hardware, a circuit and just say this circuit represents this function f, you need some way to type x in or type y in. But if you type it in and then you press a button, then it will spit out z. Okay? So that's one thing you could do. So you could do hardware, right? Anything else? So what's the analog to hardware? So software, you could give me maybe a piece of code, right? A library, and then I call that library, I put the inputs in, and then it gives me the output, okay? You could maybe do some sort of physical thing. Before the invention of computers, there were all sorts of weird things with like gears and things like that, and you could maybe implement an F that does this. Those machines are sometimes used. I work on voting technology, for example, and the New York State, until very recently, they actually had these like voting machines where you would pull a lever. Sorry, you would like press which candidate you want to vote for. You would pull a lever, and then it would like spin all these gears, and then there would be like a counter that would increase like the tally for that particular person that you pressed. Then it would reset and it would kind of open the door for you. That's also possible. Okay, of all of the things that we talked about, they're all things that are sort of relevant to the topic of zero knowledge. Well, maybe not the physical, but the hardware or software model. But the place I want to start with is the hardware or the circuits. Okay, so I want to start by thinking of this F as a circuit. Okay, what is a circuit? What does it look like?
Gates.
Okay, so you have gates, and what's a gate?
Implements logic.
Okay, so you have like a small operation. It's almost like a circuit. It takes inputs and outputs, but it's really small. It does some little thing, and then what you do is you get a whole bunch of gates and you kind of wire them up, and then you're able to do a bigger thing because you wired a bunch of gates up, okay? So, for example, we might have a circuit that we have X, Y. I'll introduce a couple more inputs. By the way, when I say X and Y here, it's just to give you the impression that it can be more than one thing, but it's not to give you the impression that it has to be two, okay? So it can be 1, it can be 100, it can be 10,000. I don't know how many inputs you're going to have. Okay, maybe I'll write it like this. All right, so a circuit would look something like this. You would have this idea of a gate, which I'll call G, and maybe these go into the gates. And then these two things go into a gate. And then we get our output, which I'll call Z, and I'll change this to a different letter. Okay, so this is more or less what a circuit looks like, all right? Okay, so what I want to do is I want to simplify things as much as possible. So what we're going to do is we're going to consider at first what's called a Boolean circuit, if you want the terminology. And it's basically a really simple circuit. And how do we simplify it? Well, we're going to simplify it in a couple ways. First off, X, Y, V, W, what is that? Like, is it a number? Is it data? It can be anything. So depending on the circuit, it can be whatever you want it to be. But arguably, the simplest circuit possible would be that those would just be a single bit. So they're either a 0, a 1, an on, off, low, high, whatever you want to call it. And so what we'll do is we'll consider binary inputs. Another question is, how many inputs can you have to a single gate? And the answer, again, it depends on your circuit. Depends what kind of circuit you're doing. You can have as many as you want. Okay, so you might have 1,000 things that go into one gate and then a couple things that come out. Okay, because we're simplifying things, the simplest, if you just have one input and one output, it's hard to make any progress or to do anything. And so sort of at minimum, you need 2. 2 is like kind of the smallest number that's reasonable. Then you can mix together your data. So we're going to consider a 2 input. And similar with outputs, you can have more than one output, but we'll consider one output. Although you could do something like maybe grab this wire and feed it into another gate. So it's it's a little different than saying it's the same, it's only one output, but you're putting it into more than one place. But for now, this diagram we'll just keep for now. Okay, and then the gates themselves, what do? Well, now we've really restricted what a gate looks like. It's something that takes two inputs. It takes one output, and I'm going to make the output binary as well. Okay, so a gate has to look something like this. So you're going to have like, I'll call it a left input and a right input. And then you have an output. And because it's binary, we can actually draw out every combination. Okay. Our left input and right input can both be 0. We could have a 0 and a 1. We could have a 1 and a 0, or we can have a 1 and a 1. That's it. There's only 4 combinations. Okay. So all this gate does is it looks at all the combinations that it could receive, and then it decides what to output. And what it output is going to be binary as well. It's also going to be a bit, okay? And so there's actually not a lot of combinations. You could actually consider all the outputs, and there's going to be 16 different possible gates. But anyways, I'll show you one, for example. So let's say I decide that if I see 2 zeros that come in, I'm going to output a 1. If I see a 0 and 1, I'll output a 1. If I see a 1 and a 0, I'll output a 1. And if I see a 1 and a 1, I'll output a 0. Okay? So that's one possible gate of all the possible gates that you might have. Okay? This gate has a name, by the way. Does anyone happen to know if you've taken electrical engineering? Okay, so it's considered a NAND gate. NAND is short for not and. And this is basically like you and it. Sorry, if your output equals the flip of an and between right and left. So if you know what an and is, it basically says both of them need to be 1. Then it's then you output a 1. If anything is not a 1, then you're going to output a 0. Okay, so that's what an AND gate does. And then what we're doing is we're flipping it. So an AND gate would look like 1, 0, 0, 0, and then we flip each of them. So it's a not and it gets flipped. Okay, but this doesn't really matter so much. Okay, so this is arguably, let's say that I do a circuit and I only have this gate. I don't even have all the Boolean gates. I literally just have a NAND gate. So every gate is a NAND gate. Every input is a bit. Every output is a bit. And every NAND only takes 2 bits and outputs 1 bit. Okay? That's one of the simplest possible circuits that you could have. Okay? So it's a very, very simple circuit, maybe arguably the simplest. Now, if I want my circuit to be more powerful, then I can start relaxing these conditions. So I can start saying, instead of just taking in 1-bit inputs, I'll take in a bunch of bits, 10 bits or a byte or a couple bytes, right? I can say, instead of just having 1 gate, I'll have 10 different kinds of gates, or I'll have 100 different kinds of gates, and different gates will do different kind of things. I'll have gates that take 10 inputs or 12 inputs, not just 2 inputs, okay? And so there's lots of ways to make this more complicated, okay? What does that buy me? If I make this circuit more complicated, what do I get as a result? Does anyone know? So not security, good guess though, given the course. Speed, okay, so that is one. So there's 2 things that you might think about. One is like efficiency or speed, or like, can I do my operation in using less gates? So the more complicated the gates are, the bigger chunks that they take in, the less of them I'm going to need to get from start to finish for the function that I want to do. Okay? The second thing is I can probably do more complicated programs, right? There's probably something, this is probably too simple for some types of things that I might want to do, and so I need more complicated gates and more complicated things in order so we call that expressivity. So like what are all the functions I can express with this kind of circuit, okay? So let's say I make it more complex. I might expect a smaller circuit for the same function f. And I might expect more kinds of f that I can use as a circuit. Okay? These are pretty reasonable things. Now, what I'm going to tell you is one of these two things is wrong. This is the most important thing that if you take circuits, if you do electrical engineering, digital electrical engineering, it's like the fundamental thing that you'll learn. One of these two things is wrong. Anyone want to hazard a guess as to which of the two is, if you don't know? Let's take a vote. Who thinks the first one's wrong? Who thinks the second one is wrong? Who doesn't know? Most people? Okay. So the answer is the second one. Okay? So this is not correct. What this says is that even though this circuit is super simple, it's arguably the simplest possible circuit, you can implement any function that you want. Any function that could be implemented with a circuit can be implemented as a circuit that's only Boolean and only uses NAND gates. Okay? In other words, this is sufficient to create any circuit possible. Okay? Is it going to be fast? No. Are you going to need a lot of NAND gates? Yes. If I want to run Windows with just NAND gates, it's possible in theory. I can do it, okay? But it's going to be a lot of NAND gates, and that's why we like to, make more gates and more things that are expressive and things like that. But everything that you do could, in theory, be done with just a big old pile of NAND gates, okay? So if I walked in and I gave you like a breadboard circuit board and a battery and lots of wires and lots of NAND gates, you could implement any function you want, assuming that like it has all these restrictions, like it starts, it finishes, it's deterministic and all that type of stuff, okay? So it could be some super complicated machine learning thing. It could be, it could be addition or multiplication. It could be go to a website and download it and look through it and try and find something that's there and try and show that it's there or check that, make sure it's there. Whatever function you want, as long as it's sort of a one-shot deterministic thing, you could implement with a big pile of NAND gates. Okay. All right. So this is going to be very useful for us as we go to zero knowledge. All right. So NAND, Boolean. I'll keep it in red because it's an important point. Sorry. Yeah. So let's say that, say there is a function that I want to implement. I'm going to have to use a lot of NAND gates to do it, right? Because they're very simpler. They're only taking one input and one output. If I relax any of these conditions, so I'm allowed to take larger numbers in, or I'm allowed to, my numbers can be bigger than bits in terms of inputs or outputs, or I can have more outputs for each gate. Then all of those things might allow me to, say, use one gate to implement something rather than using, wiring up 20 NAND gates in order to do the same thing. Yeah, I can see you're skeptical. So give me 1 second, and I'll give you a concrete example of what that is. Okay. All right. So Boolean circuits with only NAND gates. Can implement any circuit. Okay. Now, if this seems unbelievable to you, there's a similar result actually for software. So if you think of software, you have programming languages, there's all sorts of different functions that you can call, and then your programming language gets compiled down to what's called assembly. And assembly is like kind of the operations that a computer uses. So like a RISC-V architecture has a certain number of assembly operations, okay? And there's all these assembly operations or opcodes because you want your computer to be fast. But let's say you go through and you start erasing. You're like, I don't want that opcode. I don't want that opcode. You start throwing them out, right? How many opcodes could you get down to where that computer can still run any program that it could before? It just might not be as fast, right? And so the answer is you can get down to a single opcode. So like, for example, there's an opcode called branch not equal. That is complete. So the term we use is Turing complete. So Turing complete just means that if all you have is a branch not equal opcode, you can run any software. You can program your thing and compile it down to just a bunch of branch not equals. It's going to be super slow and super inefficient, but you can do it technically. Okay, so so this is kind of like Turing completeness, but it's for circuits, not for software itself. Okay, now in this course, I just gave this, yeah.
Why NAND gates are special in this case? I mean, other than NAND gates, can we use something else, or NAND gates are special?
Okay, good question. So why is the NAND gate the special one? So there are a couple other Boolean gates that you can use as well that are also complete. And then there's some that are like very common ones that are not complete. So for example, trying to think. I want to say an and an or is complete, but if you just have and, for sure, if you just have and you just have or, then it's not complete. If you just have XOR, it's not complete. So one thing that and or both are is that we call them threshold functions, because when you look at their truth table, this is called a truth table, by the way, if you want. So an and would be 0, 0, 0, 1, and an or would be 0, 1, 1, 1. They're all like kind of linear, like they if you kind of visualize it as you go down the table, they kind of start at 0 and then they jump up to 1, or they start at 0 and then they jump up to 1, but there's no like backward jump kind of thing. So we call these threshold operations because they hit a certain point and then they jump up. So at a minimum, you need something that is in a threshold. So it doesn't start low and then just increase. So that's like one minimal connection. So NAND has that property, but that's necessary, but not necessarily sufficient. But yeah, but anyways, the other thing you can do is that you can show that every other gate that's possible that's Boolean, you can implement with a bunch of NAND gates. Yeah, so like let's say that you want an XOR, you can put 2 or 3 NAND gates together and you can get an XOR operation out of it. I don't know off the top of my head like how to draw it out, but that is possible. Yeah.
Can you have a break?
Break, yeah, so let's see, what time is it? 1, yeah, it's actually a great time. Okay, let's go for 10 minutes and then we'll come back. Okay, so before we saw Boolean circuits, they're complete. We won't actually use Boolean circuits. I just wanted to kind of motivate this idea of like you just need a small number of gates and simple circuits. We're going to use something that's slightly more complicated. but it's also complete as well, and it's something that's going to be a little easier when we want to do cryptography later to use. Okay, so so I'm going to talk about something called an arithmetic circuit. Okay, so arithmetic circuits are like a Boolean circuit. So like Boolean circuit, they are this. So sometimes we call this complete or universal. Okay, but they also have this property that anything you can implement with NAND circuits, you can implement with arithmetic circuits, and vice versa. Okay, and any other kind of circuit. Okay, so an arithmetic circuit will also be 2 input, 2 output gates. Or sorry, 1 output gate. We're going to have 2 kinds of gates though, not just 1. Okay, 1 gate is going to be called an AND gate. And the other gate we're going to call a multiply gate. I'll just put addition and multiply for now. Okay, and the inputs we're going to allow bigger numbers than bits. Okay, so we're going to take an integer, for example. So the inputs will be integers. I'll talk a little bit about some of the details of that. And similarly, the output as well. Okay, so again, we're going to have a very simple circuit. X, Y, B, W. And now what we're going to do is we're going to have 2 kinds of gates. So maybe we want to add this together. And maybe we want to multiply these. And then we'll take whatever comes out of these 2 and we'll add them together. And then whatever comes out there we'll call our output. Okay? All right, so this is also sufficient for any circuit. So anything you want to program that's like a one-shot, deterministic, all those restrictions, you can also do just with additions and just with multiplications. Okay, that's all you need. Okay, you might need a lot of them, a lot of additions and multiplications, but you can get whatever you want into just additions and multiplications, also with 2 inputs and 1 output. Okay, so the AND gate is what you think it is, almost what you think it is. So the output is the left input plus the right input. Okay, and a mult gate, the output is going to be the left input times the right input. Okay, now there's going to be one small twist. Okay, it's going to be a twist that we'll spend next lecture on. So if you don't know what it is yet, it's okay. But the problem with just having this right now is that the output's going to get bigger and bigger and bigger. Okay, when you start multiplying things and it's just going to get bigger. And if you want to implement this in hardware, you have to store numbers and you have to store it somehow. So you have some sort of register, flip-flops if you think at the circuit level, whatever. You have some way of storing it, and storage has limits. Okay, storage isn't infinitely big. Okay, so what we want to do is we want to clip values that get too big. Okay, so once they get too big, what we do is we actually kind of wrap them back around. So they kind of overflow and then they wrap back down to a smaller number. Okay, and when we write this down mathematically, we use an operation called a modulus. Okay, so I'm going to write mod q, where q is a number. Okay, so this is a largish number. For reasons that we'll get to sometime much later, this will be a prime number, but you don't have to worry about why that's the case now. And a modulus is an operation, even if you don't know, if you don't recognize it, you could understand what it is. It's basically you divide by q. So you take whatever the number is here, and you divide it by q, and keep the remainder. So you throw away everything else, and you just keep the remainder. Okay, and we'll talk a little bit about this operation later, but today we don't have to worry about it much more than that. Just, I want you to know that it's not exactly straightforward additions and multiplications. It does have this restriction, okay? And when I say integers here, I also mean whole numbers, not as opposed to decimals. So it's not 5.3 times 4 or something like that. We're only going to deal with whole integers, no like complex numbers or anything crazy like that, okay? For a modulus, the example that's usually given, although it doesn't map exactly perfectly, is a clock. So times are always between like 1 and 12, or 0 and 11, depending on how you count. And minutes are maybe a better example. They're between 0 and 60. So like, let's say it's 134 or 123. And I want to add 5,000 minutes to that time, right? And I just want to know like what minute is that? Like what minute past the hour is that? Then I would use a modulus. So I would do the addition. I would mod it down by 60 because there's 60 seconds in a minute. And then whatever the answer is, I would divide by 60, take the remainder, and then it would tell me, okay, that time is between, it's at whatever time 45, like it's at 1:45 or something like that. Okay, I didn't explain that very well, but anyways, clocks are kind of like that. Once you hit 12:59, then you wrap back to 0, or noon. Or if you're thinking of a 24-hour clock, if you hit 11:59, then you wrap back to 0, 0, 0, 0, 0. Okay, so that's what a modulus is. It just kind of keeps wrapping. Every time you hit Q, you go back to the start. And then you hit Q again and you go back to the start and you keep cycling around, okay? This is important in cryptography for reasons that we won't get to today, but maybe by tomorrow. Okay, so an earlier question was, if we make the circuit more complicated, why does it make it a smaller circuit, right? So actually just think of adding two numbers. So if I do X and Y and I want to add them, and let's say that they're, I don't know, like 4 bits long. If I have an add gate, I put them in the add gate and I get the answer right away, okay? If I just have NAND gates, I can still do the addition, but I'm gonna have to do it bit by bit, and then I'm gonna have to like carry the bits and things like that. So you can see, I won't draw it out, but you can see that it would probably involve at least 10 gates to do that, yeah? So this is why we made it a little more powerful by having stronger gates, more than one type of gate. We let the inputs be a little bit bigger, and now all of a sudden I can do this operation in one gate instead of 10 or whatever, yeah? So generally in computer engineering, the more variety of gates that we have, the faster that we can do things. And if there's operations that are really important that a computer does a lot, then what Intel will do is they'll make a gate for that operation. And then what you can do is now the computer can do that operation in a single second, okay? So there's all sorts of like machine learning, like relevant things. There's lots of graphics things, like you get a graphic card, it's gonna have vector manipulations or whatever. For cryptography, you might have something like a hash function, and now you can do a hash function in a single clock cycle because Intel did the whole circuit. Maybe not quite a gate, but they have a whole circuit that they can execute in one clock cycle just for that hash function kind of thing. Okay. In this course, what we're going to do is we're not going to go much more complicated than this. Okay. Later, I'll talk about how you can make the gates more complicated if you wanted to. But because this is sufficient, because I can implement any function which just adds and multiplies, all we're going to focus on is how can we just get adds and multiplies working. how can we get a circuit working with wires and adds and multiplies? And if we can get that working in that environment, then that can do anything else. Okay? So, but anyways, I haven't really said what does it mean to get it working or what it does. So at this point, I think it's good to now talk about what exactly zero knowledge is, or a zero knowledge proof. Okay, so I'll draw the same picture I had before. I have some function, and now I'm going to think about it as a circuit. Okay, so it's some function that's implemented as a circuit, an arithmetic circuit. Okay, and anything that I can implement as a circuit, you can use F for. So this F can be anything, even if it's 10. It's actually better. The bigger the circuit, the better this technology is. So if you have 10,000 gates, that's great. You want this technology for that. So we're not talking about little dinky things like adding numbers together. We're talking about like really complicated things. But anyways, we're calling this a circuit. We have some inputs. We have an output. Circuit is going to be deterministic, again, just meaning same inputs will give you the same output. If you care about circuits, you might say, well, can I kind of loop, like can I wire an output back into an input? So you're not allowed to do that kind of thing. So it's going to be a simple circuit that just goes from start to finish. So there's no loops. But if you want to do something 5 times in a row, you can do it. You just have to, it's like in programming when you uncurl a loop. Instead of looping 5 times, you just make 5 copies of the same code and you just do it 5 times sequentially. Okay. All right, now let's introduce 2 people. So in cryptography, we often talk about Alice and Bob. So here's Alice, here's Bob. And Alice says, I have this function f, and when I run the function f on these 2 inputs, x and y, I get z. That's the output that I give. Okay? So Alice sends to Bob z, f, x, y. So Bob now has everything he needs in order to check it. And in cryptography, we usually think about trust. Like, do I trust other people? But people tell me stuff, do I trust it or not? So let's consider this case where Bob doesn't trust Alice. Okay, so Alice is telling Bob z is the output of this function. Bob does not trust that. Okay, he thinks maybe she's lying. All right, what can Bob do in order to check? Okay, and what does that mean? Okay, so Bob knows everything he needs to know, right? So he can just rerun it himself, and he can see whether or not the output matches. We agree? Okay, so what Bob can do if he doesn't trust Alice is he can run f, which he has a copy of, on the input x and the input y, and he can ask, is the output of this the same as the z that Alice sent? And if it is, then I'm happy this checks out. Okay? All right, so this is a good world to live in. Up until f is really complicated. Let's say f is something that takes, you do it on Google Cloud because you can't even do it on your PC or your notebook, let alone your phone, and it takes 6 hours of compute time. And I want to check this on my phone. I just have a phone. Okay? Can I recompute it? I can't. Even though I know what to do, I know what f is, I know what the inputs are, I know what the output is supposed to be. I just don't have the time, the resource, the battery life in order to recompute it myself. Okay? So is there something else that we could do in that scenario? So what we can do is we can live in a world where Alice will send to Bob Same thing. They'll send Z, they'll send F, they'll send X, they'll send Y, and they're going to send a proof. Usually we use pi. And the proof pi just says that Z is the output of F applied to X and Y. Okay? So I give you a proof that Z is correct, and then now you don't have to rerun it. Okay? But you do have to do something, which is you have to check the proof. Okay? So Bob gets the proof. Now he has to run some function, which I'll just sketch out. We'll write it out more formally later, but you can think of it as a function called verify, and it basically is going to verify the proof, usually with a copy of all the inputs and outputs, but I'll write it simply as pi, and it's either going to say yes, it's correct, or no, it's not correct. Okay? All right. How do we do these proofs? I don't know. Just pretend by magic. Somehow there's a magic way that you can prove to someone that you can do it. Okay, I don't know how to do it. But for a second here, which is a better world to live in? Would you rather recompute it yourself, or would you rather check a proof? Why do we think we want to check a proof better? Because it's faster, okay? So, but that is a condition, okay? So I planted the seed in your mind that, this was a big, expensive computation. So in that case, you would much rather verify the proof. But if F is really simple, like say it's just adding two numbers together, then actually maybe it's easier to just rerun it yourself, okay? So whether you prefer kind of like, we'll call this like world 1 or world 2, it's going to depend on how complicated F is, okay? But at a certain point, when F gets sufficiently complicated, you're going to want to switch to world 2, probably. But we haven't said, I haven't told you how fast it is to verify the proof yet, okay? But our intuition is that probably at a certain point, it's going to cross over, it's going to be cheaper to verify the proof, okay? So the way that we do it is what we call a zero-knowledge proof. So that's what this course is about. So zero-knowledge proof is pi in this diagram. So it's the same as what pi is. So this whole course is about how we can do that. How can I prove to you that the output of some function is correct, even though that function could be really, really complicated? And because I can't talk about all the possible functions, there's too many different kinds of functions, I'm going to lean into this result about circuits. And what I'm going to do is I'm going to convince you that I can prove to you that this output matches these inputs if you just have a bunch of add and multiply gates. Okay, so if you can write down what you want to prove in terms of a circuit of a bunch of gates, then I have a method that can prove that the add gates are done right. I have a method that can prove that the multiplication gates are done right. And I have a method that will prove that everything, if you say it's wired up, these gates are wired to these ones, all the wiring was done correctly. So the output, for example, the output here is truly copied into the input here and things like that. Okay? That's basically all I prove to you, and then you now have a proof that covers every single possible circuit. Yeah?
Just, I want to make sure I'm understanding.
Yeah.
So in this example, Bob is believing Alice that the numbers that they sent were computed using that function.
Correct.
So, because if those numbers are just imaginary numbers that were put in randomly, proving that the function works as intended isn't useful anymore. But we're assuming that those numbers
So
are real numbers.
what this proof will do is, when you get the proof, you'll also get a copy of the numbers. So what you'll do is you'll look at the numbers,
Yeah.
and you can decide. That's a separate question of do these numbers match my reality of what I think it is? Yeah. And if they do, then the only thing it really saves you is you don't have to execute F yourself, because you know that Z is correct. Yeah. So there's two kind of meta level questions. right? So one is like, are these inputs right? Like, do they correspond to what I'm thinking this proof is about? And you can say the same thing about F2. Does this circuit actually implement what the person's saying it implements? Yeah? And so those are two checks that you would have to do kind of at the meta level. And then what this proof is just going to cover is strictly that Z is the output of this function applied to X and Y. Got it? Yeah, okay. Okay, so zero knowledge proof here is pi. Now let's go back to the question of would I rather be in world 1 or world 2? It's going to depend on how expensive this verify function is, okay? If this verify function is cheap, then I would rather be in world 2 for almost all functions. And if it's expensive, if this takes eight compute hours on cloud computing, then maybe I just want to stay in world 1, okay? So what we have now are what we call succinct I'm going to abbreviate this to ZKP. And so we have succinct ZKPs. And a succinct ZKP is one where pi is small, or short. Short's a better way of putting it, okay? So the length of the proof is going to be short. I will define what short means in a second. And verify is fast. Now there's different technical definitions of how short and how fast does it have to be before you can call yourself succinct. So instead of weighing you down with that yet, we'll consider that later, I'm going to tell you what Planck does. Okay, so Planck gives you. In Planck, what a short proof means is it means it's a couple kilobytes. And the size of the proof has nothing to do with how many gates there are in the circuit. So you could have a circuit that has 5 gates, or you could have a circuit that has 5 million gates, and the size of the proof will always be exactly the same. Okay? So if we think of the number of gates as n, it's the main determinant of how fast or slow these things are. Then sometimes we write in complexity theory like big O. So this just means that it runs independent of n. It runs in constant time. So it's a constant operation. Sorry, I flipped to talking to time. I didn't mean to do that. The size of it is a constant. It will always be the same size, okay? And the same thing will apply to the verify function itself, okay? So the verify will take, milliseconds, like under a second, and it also will always be the same amount of time. Doesn't matter how complicated the circuits are, okay? So very, very earlier on, I talked about how in the 1980s, we had zero knowledge proofs. Everything we do in this class we could have done in the 1980s. The problem with it is the more gates you have in the circuit, the bigger your proof gets. So if you have 10,000 gates, your proof would be size 10,000. And if you have 1 million gates, then your proof is going to get 1 million. And to check it, you have to go gate by gate. So you also have to check it. Now we can do everything constant time. Yeah.
So you mentioned that it was kind of brought about in 1980.
Yeah.
Can you please explain why did they create zero knowledge proof? Like what was the reason for its invention? Like what was it solving? And like how can we tie it to like the use case, for example, the proof that you just spoke about, how they like kind of correlate and all that?
Okay. So it does the same thing. So as far as this picture is concerned, 1980 is exactly the same. So nothing about this picture is different, with one exception, which is just that verify takes really long. So now, yeah, your question, it's actually, let me come back to it like maybe in 10 minutes. Because there's something else that we're missing. There's another big piece that we're missing. And when you see that piece, I think it will make more sense. Yep? Okay. All right. And yeah. So actually, in lieu of that, I'm wondering maybe I should change the language here a little bit. So I'm just going to call this a proof. just call it proof, as opposed to a zero knowledge proof, because I'm going to distinguish that term in a second. Also, the technical term we use is an argument. An argument's exactly the same as proof, but there's a theoretical difference that I don't want to weigh you down with now. It doesn't really matter. But anyways. Okay, so I'll just call this proof or argument for now. Okay, and then back to world 1 and world 2. Basically, you can kind of think about, here's like the number of gates in F. And so for a while, like the more gates, the more gates there are, the longer it takes you to run, right? So for a certain period of time, you'll be happy to just re-execute the circuit. So you get the inputs and you just rerun F and you get Z and you just replicate it and make sure that it's right, okay? So this is kind of like world 1 as the gates go up. And then at a certain point, it's going to be cheaper to run verify than to check more gates, okay? So at that point, you're going to prefer to be in world 2. This is the amount of time that you spend. And it's also space, like the length of the proof as well. So like, because you have to communicate everything as well, but times, we'll just consider time for now. Okay, so maybe it's only 3 gates. I'll just keep re-executing it. Now it's 300 gates. It's still cheaper to re-execute it, but now it's 3,000 gates. It's cheaper to actually verify a SNARK. And so what I'll do, or a proof, I should say, and then what I'll do is I'll switch to world 2, and then from that point, as the more complicated F gets, the more and more I'm saving by being in world 2. Okay, so world 2 looks really, really great when the Fs are like really, really complicated. Okay, what else do I want to say about this? The other thing about a proof is something that you probably wouldn't even think about unless if you had been steeped in a lot of cryptography. But the proof is just something you check. It's written down. You get a copy of it. You check it. And that's it, okay? Now, why am I saying this? It seems sort of obvious. What's the other alternative to that? Well, there are some proof systems that are interactive. So Alice and Bob would have a conversation. Alice would say, I don't quite believe you. I'm going to give you a random challenge, and I'm going to challenge you, and then I'm going to check this thing. Oh, you didn't lie about that, but now I'm going to check something else. And they might go back and forth, and then at the end, Bob's like, okay, now I believe this is true. Okay, so those are called interactive proofs. In the history of computer science and proving things, lots of proofs are interactive, but these ones are all, at least there's a way to make them non-interactive. So they will kind of be interactive at first, but then we'll figure out how to make them non-interactive. Okay, so we're doing pretty good. All right, now there's one variant on this scenario that I want to show you. And this will help answer the question of why it was useful in 1980s. So same picture, almost. We have Alice, we have Bob. We have some function, z equals f of x and y. For reasons I'll explain in a second, I'm just going to shift y to w. Okay, but it's just a symbol at this point, just because it will match the name of what we're going to call this. Okay. And what Alice is going to do is she's going to send to Bob z, the output, the function f, the input x, but she's not going to send the value y, or sorry, w. Okay, where w is going to be a secret. Okay, so Alice knows she's thinking about some value w, and she knows a value of w that would produce this output if you run it together with x through this function. But she's not going to tell Bob what it is. Okay, so Bob doesn't know what it is. All right, Now, do we want to live in world 1 and world 2? Well, we can't actually live in world 1 anymore because Bob can't reproduce that computation because he doesn't know what W is, okay? So Bob in world 1 tries to see whether, sorry, I wrote it like that. So he wants to know whether Z equals X and W. The problem is W is missing. I don't know what that is, okay? So world 1 doesn't work. I can't check it. But world 2 does work, okay? So everything I said about world 2, you can also do in the situation where you're not telling all the values. Right? So Alice will send Z, F, the inputs that are known, the public inputs, and a proof. And Bob will run verify on the proof. And make sure that it returns true. Okay? Verify will still run in O1 time, constant time. O1 is just a fancy way of saying it doesn't matter how many gates there are. It's always the same amount of time. The length of the proof will still be O1. For Planck, in general, we're happy to call it succinct as long as it's under linear. So if it's linear, we say that's not succinct. If it was like logarithmic in the size of the number of gates, and sometimes you might think about, is the time and the length always the same? So let's say the length isn't constant. Let's say it's some function of n, like say logarithmic in n. Then you have to read that entire proof. If you didn't have to read it, then you wouldn't have to send the whole thing. So you can make the proof shorter. So if you have to read the whole proof, the amount of time you spend has to be the same as the length of the proof. Okay? So the amount of time that you spend has to be at least the length of the proof just to read it. Okay? So the amount of time can never be less than the length of the proof. Most cases they're going to be equal, but there are some protocols where it's more. So you read it once, and then you do some stuff, and then you have to read it again, and then you have to read it like a certain amount of times, and then so the amount of time that you spend ends up being more than the length of the proof itself. But anyways, in the Planck world, it's all going to be constant. It's super simple, and we can think later about differences there. Okay. Okay. Now, what does it mean to verify that this thing is true? Okay, we said we verify that it's true, but like if I don't have one of the inputs, what am I verifying exactly? Like what exactly is being proven here? Okay, so something's being proven, right? What exactly is it? Can I say out loud what it is that's being proven? It's a little weird. It's phrased a little weird. And this is the challenge with zero knowledge proofs is you have to go out in the real world and you have to see how things in the real world are going to fit this way of phrasing it. And I'm going to give you a whole bunch of examples. In every class, I'm going to give you an example as well. And it will take a bit of time maybe for you to sort of, it takes me time too. I have to stop and think about it a bit. But this is the statement that's being proven that looks a little weird, but it's actually very powerful. Okay? So basically what Alice is saying, Alice's statement that she's proving, I know some value W such that Z equals f of x and W. Okay? So she's proving knowledge of some value. She can't tell the value because it's a secret. So what she's proving is she knows some W that would satisfy this equation. Okay, so there's this equation, there's this f function. I know an input to that function, and if you were to run that function on it, then Z would be the output. Okay? All right. So when one of these inputs is private, we call it zero knowledge. Or a zero knowledge proof. Okay? And one of the strict properties of the proof is that pi does not leak any information about W. Okay, so you can look at this proof. You know Z, you know F, you know X, you know everything except for W. But now that you have a proof that W is correct, or at least Alice knows it, it's not going to reveal any information about W. It's going to reveal zero information. It's going to give you zero knowledge about what F is. Okay? So that's what that term zero knowledge means. It means I get zero knowledge about W by looking at this proof itself. Okay? So I want to do some examples, but before I just want to lock down some terminology. So I'll keep drawing the same thing. So here's F, here's X, here's W, here's the output. The number of inputs can be any number you want. So I'll put ... just so you can have a whole bunch of X's and a whole bunch of W's. I'm just trying to keep it simple, that's why I'm showing two, but you can have more than one you want. Any input that Bob knows, that you tell Bob, we call a public input. So this is the public inputs. I'll put it plural just to imply that there can be more than one. And this is your private input, or inputs. You can have more than one. And the term that just goes back to like 1980s cryptography is called witness. And this reminds me of the question earlier. So the question earlier was, in the 1980s, if we can't do this verify succinctly, then why even bother? Well, the answer is because sometimes we want to prove things about secrets. And so even if this took like a linear amount of time or some really long time, it's the only way that I can convince you that I know this value, because I can't hand you all the values itself. Yeah. So in 1980s, they came up with proofs. This whole picture, the only difference was that the amount of time it took here was basically linear in the number of gates. And then recently, we were able to get it constant. Yeah.
Do you have a real life example?
I do. I have 10 of them coming. Yeah. So, okay. Let me just standardize this, and then so I can show you some real life examples. Okay. So this we call the output. Public inputs, private inputs. Witness, sorry, is the word that was used. It's kind of a weird word, but we say it's a witness. Okay. And because, and then we have the proof itself. Okay. The proof itself is succinct. So constant time to verify. Now, one thing I'm cheating a bit is, how long does it take Alice to write this proof? So we just talked about Bob. Bob gets to check it. It's short, and it is constant length. But Alice has to make the proof. The proof takes a long time to make. Okay, so it is easily linear in the number of gates. So if you have 10,000 gates, you're going to have to do something 10,000 times. But usually it's more than that. It might be n log n squared, something like that. So there's a kind of trade-off here happening. So Alice is spending a lot of time making this proof so that Bob doesn't have to spend a lot of time verifying it. Okay, so that's another component that we'll get to later. Okay, so the proof is succinct, constant time to verify. We call this a succinct so it's succinct. Like I said, the proof, you just get it, you check it, you don't have to go back and forth. Yeah.
Sir, I'll just need to ask, does Alice know, is Alice the only one who knows about W, the private input, or Bob also knows what W is?
So only Alice knows about W, and Bob does not know W. And even at the end of checking the proof, Bob doesn't learn any more about W than he did before he started. Yeah.
Is it not missing?
Is what, sorry?
Is it not word missing exactly at the last line? It's not on last line.
Here? Does not. Yeah, sorry, thank you. Thanks. Okay. Okay, so this is succinct. It's non-interactive, meaning you just take a look at the proof. And when you prove, I know a W that satisfies this, I call that a proof of knowledge. So it's a proof of knowledge of a witness. It's kind of a weird term. And for technical reasons, it's an argument, not a proof. But it's going to be an argument of knowledge. And if we put these three things together, you get an acronym, which is SNARK. And so that's what these things are called. Okay, so zero knowledge proofs is the umbrella term. It includes everything in the 1980s and the modern thing. The modern thing where the zero knowledge proofs are really short and easy to verify is called a SNARK. Okay, SNARKs come in two flavors. You have what is a SNARK, and then you have the ZK SNARK. And a ZK SNARK is the one where there's a witness, there's a private input. And just a SNARK is just where all inputs are public. So you have the option of re-executing it if you want, but you prefer the SNARK because it's faster. Okay, so sometimes we distinguish between the two. There's use cases on both sides. Lots of use cases on the ZK SNARK side, but there's a lot of use cases too where you just want to verify that computations were done correctly, and you could, in theory, re-execute it. You just don't have time. I don't want to waste time doing it. If someone's willing to give me a proof that it was done correct, much rather verify the proof, okay? Or there's scenarios too where like, maybe there's one person that's doing the proof. Like there's scenarios where there's Alice and Bob, they're two people. There's also scenarios where there's 1,000 Bobs, right? And so it's better for Alice to spend a little time making this proof so that 1,000 people can save time checking the proof, kind of. Okay. Okay, so let me give you some examples, quick examples. We don't have much time. To try and convince you that this is like a useful thing in real life. And we'll try and think of what does that mean, like proof, knowledge of, like what does that actually mean? Okay, so I'll give you a simple example. So I'm gonna write statement, which is just like an English description. I am over 18. I'm going to a bar. I want to prove that I'm over 18 so I can get into the bar. It's 18 in Quebec, I think. So that's my statement that I want to prove. Okay. I have some inputs that are public. I have some private inputs. Otherwise the witness. And then I have the function f that I'm running itself, okay? If I want to show that I'm over 18, normally I would show a driver's license, okay? So I can show the driver's license, that's the input. The function is basically like find age on this driver's license, or actually find the year. Actually, I guess you need more than the year strictly if you're close to being 18, but find the date, subtract 18 years from the date, and is that greater or less than today's date, okay? So that's more or less what the function is. So it's like find the age, find the birth date, add 18 years, and then is the result less than today's date. Okay? Now, if I show the driver's license, that's a normal SNARK, not a ZK SNARK. It's the kind of thing that it's probably way easier to just check the driver's license than to try and do this whole proof thing. Okay? But what if I don't want to show the driver's license? Let's say I have a digital copy of the driver's license, okay? And it's autographed or signed digitally by Quebec's government. Then I could say, okay, I'm not going to show you the driver's license itself. The license is going to be a private input. The only thing you need to know is like what does it look like if Quebec digitally signs something? So digital signatures is this thing in cryptography. You have a key, a public key, and so that's the value that you need. So I need Quebec's public key. And then I can write a function that basically says, I know of a driver's license that exists that if you were to find the birth date at 18 years, the result would be less than today, and it's signed by this public key here, by Quebec. Okay? So I know that that thing exists. I'm not showing it to you, but I know that it exists. Does that prove that I'm over 18? It does, because it couldn't exist if I wasn't over 18, right? Either I wouldn't have it, or I would have it, but the birth date wouldn't satisfy that condition, or I would have it, but it's a fraud or something, so it's not actually signed by Quebec, it's signed by someone else. Okay? So if all of those three conditions hold, that license can only exist if I'm over 18. Okay? Now, we should actually make it a little more complicated. So you also would have to match that to my face, I guess, right? Because I could show you my friend's driver's license. And so what we can do is we can add the photo to the public input, and I can prove to you also that the photo matches what the photo that's on the driver's license itself. So that would be a way of making it a little more robust. Or it's a necessary condition. It wouldn't work without it, okay? So the public inputs are, you have to see the photo because you have nothing to compare to it. You have what Quebec's signature looks like. I don't show you the license itself. I just prove to you that I'm over 18 without disclosing it as well, okay? Sometimes we call this minimal disclosure because it's, you're minimizing what you're disclosing. You're not showing your address, you're not showing your name or anything like that. You're showing the bare minimum in order to get it. Okay, does that make sense, roughly? Okay, let's think of some other ones. These, I won't write them out like in full technical detail. It's just to give you kind of the flavor of things. Okay, let's say that okay, so this picture from the news is real, not AI generated. Okay, this is an example of not a zero knowledge thing. Okay, there's not going to be any secrets anywhere. Okay, it's going to be something that you could check yourself, but we're going to use SNARKs because it's going to make it easier to check. So it turns out that most cameras nowadays, high-end cameras, they actually have cryptography in them. And so every time you take a picture, it gets digitally signed. And the key is like in the hardware of the camera itself. It's hard to extract that key from the camera. And that key was put there by Nikon or I'm blanking on the big camera companies' names, but it's put there by the manufacturer of the camera itself, okay? So that exists. So when I take a picture for the newspaper, it gets digitally signed by the camera. I could show you the picture and I could show you the signature, okay? So the input could be the picture, the signature, and you could check and say, yes, I see that that was signed, okay? It doesn't quite prove that it wasn't AI generated. For example, I could generate something in AI and then take a picture of it with my camera, right? So like, but anyways, we're gonna not like split little details about that, okay? Now there's one problem, which is that normally you don't put the raw picture in the news article because these things take, 5 megapixels or whatever, something even higher than that. The size of the picture is huge, right? It's way bigger than the data on the website, all right? So what you want to do is you want to give like a smaller JPEG version. You want to compress it. You might do some editing to it. You might crop it, okay? So what we're getting here is not the original picture, okay? we're getting a compressed maybe cropped or edited, slightly edited version of the picture. Okay? What we're missing when we have this news article is I'm missing the raw picture itself. Okay? So I'm going to consider that a private input or a witness. But in this case, it's not private because it's secret, right? Like the news organization might send it to you anyways. Okay? It's just private because it's too big. It's too big to circulate on the web. All right? So I don't have the raw input. But what I can prove, what the newspaper could do, is for every, you could have a picture, you could have a caption, and then you could have a proof sitting there, not in plain text, but your browser could do it, right? And it could look at that proof, and the proof would basically say that there exists some raw image, right? So there's a raw picture that went through only the following operations: crop, recolor, compress, whatever you want, okay? Because if you manipulate it too much, then it might as well be fake. But there's some raw picture, it exists, I know about it, I've seen it. It only went through these things, and then after that, it produced the picture that you see, okay? And that raw picture was signed by the camera. Okay, so you have a function, it takes in the raw picture, it finds the signature, it checks the signature. What the other thing we need here is the key for the camera as an input. Okay, and so you take the picture, you check that the signature is correct. You're allowed to do certain manipulations to it. And when you do that, it results in the picture that everyone's looking at on the web. Okay? Then you could imagine a web browser. Every time it sees one of these pictures, it looks for a proof. If it sees the proof, it overlays a check mark, or the browser puts something on it, or maybe if you hover your mouse over it, it says this was verified. And now every time you're like on the internet, you're not on a news site now, you're on Reddit or something like that, and you really don't know whether it's AI generated or not. You just sort of hover your mouse over it and it might say verified, okay? And it was very cheap for you to do it. All you did is you downloaded this kilobyte proof, you took a millisecond to check it, and now you know that this thing was verified. At least it was generated it came from a camera that signed it, okay? All right, so that's another example where people are believing that zero-knowledge proofs are something that you might see in the next 4 or 5 years, just built into the web everywhere. Okay, questions about these two examples? Yeah.
How do you verify that it's actually the camera that's
How do you check that it was?
like the camera that's like is it possible that cameras are generating different signatures for each of the pictures we take with them? But
Yeah.
it's the same like signature for every photo,
Right. So this is it's a question, we call it PKI, public key infrastructure. But the answer for there's different ways of doing it, but this is how it would do it. Every camera would have its own key. So every time you take a picture, you would get a unique signature for that picture. But if you took 10 pictures with the same camera, they would all be signed by the same key. But if you took 10 pictures with your camera, I had the exact same model of camera, exact same brand, and I took 10 pictures, we would have different keys. Okay, so the key would be there. Then what will happen is Canon, who makes the camera, they'll sign that key with Canon's key. Okay, so what everyone will have is a copy of Canon's key. And you'll look at one of my pictures, you'll say, okay, I see it was signed by some key, and that key was signed by Canon's key. Therefore, I believe it came from a Canon camera. And then your pictures will have a different middle signature, because your key will be different, but your key will also be signed by Canon. And so that's called a chain. So you chain it back. And then Canon's is called a root certificate. So you can think of a tree where like Canon's keys at the top, you have all the cameras have their own keys, and then all the pictures have their own signatures from that key from Canon's key kind of thing. Yeah. And then sometimes the chain's longer. So Canon might have a different key for every model, and then another key that for the brand, or Canon US has a different key than Canon Europe or whatever. Yeah. But yeah, that's a good question. Okay, other questions about these two? Okay, so I wanted to give you like 10 to like really motivate you, but we're out of time, so we only got through 2. But at least you can sort of see now, if we move away from all this talk about Boolean circuits and stuff like that, this stuff, hopefully you can see it has real life applications. And this is really just scratching the surface. There's lots of other things that you can do if you can fit them into this template.
Do we agree that an example 2 would rather be in World 1? Where we could just put a link where you can click and find the original picture?
So the size...
It's kind of harder to just using the proof and keeping the raw input a secret.
Yeah, and by harder, do you mean like to understand conceptually, or you mean harder for a computer?
I mean the verification is just more complicated for the one who wants to verify Bob.
Yeah, okay, so let's just sketch this out here quickly. So world A, world B. So the proof is independent of how complicated the function is. So I made this function really complicated, but for your browser that's downloading the picture, you get a kilobyte proof, and it takes you 1 millisecond to verify. And it doesn't matter how complicated this is, yeah? I could give you a link to the original picture. You could download it. Pictures could be gigabytes if they're proper pictures, like full resolution from like a journalist's camera, yeah? And so even downloading this will take seconds, if not minutes, yeah? And then, and then checking it would be probably similar. Once you have a copy of it and you have the signature, it's pretty fast to check. But the bottleneck here is downloading all that data. So, yeah. So World B is better in this case. Yeah. And this has nothing to do with secrets. It's not like I don't want to show this to you because I'm hiding it. It's just I don't want to show it to you because it's just too big kind of thing. Yeah. So this is the first one, the over 18. I don't want to show it to you because I don't want you to know my name and address. So that's like a ZK snark because I have a private input. The second is just a snark where I'm happy to show it to you. It's just you don't have time to look at it, so I'm going to give you a proof instead. Yeah. Okay, other questions? Yeah. They're just 2 of millions. Yeah.
Hiding witness.
Oh, sorry. Yeah. So every use case can be reduced to either all the inputs are public or some of them are private. So they'll all be either in bin A or bin B. Here.
For the private ones, do we hide it because we want to hide it? And in some cases it's expensive. Is there any other option for here? Any other?
No, exactly. So you either you hide it because it's too expensive, or you hide it because you don't want the other person to know about it. Yeah. So here you don't care about whether it leaks zero knowledge about the raw input. So when you do the proof itself, you can relax a few things because you're not like sweating about like, am I leaking partial information? But generally the difference between these two is negligible. So like the cryptography to do this and the cryptography to do this is almost exactly the same. It's just really small differences that are very minor. Yeah. Okay, I think we're out of time. So I'll see you all next week. Hopefully I'll see you all next week if I didn't scare you.